So we'll look at the functions of the urinary system, specifically the kidneys. We'll look at the renal exchange process. When I say renal exchange process, you should be thinking filtration, reabsorption, secretion. Those are the three processes that have to do with renal exchange. We'll look at the specialized tissues in each part of the renal tubules, so the different characteristics of the different parts. So what's unique about the proximal convoluted tubule? What's unique about the leukopenny? What's unique about the distal convoluted tubule, etc. Excretion we're not going to look at, and again, I'll point that out when we get there. All right, so some of the main functions of the kidneys, we can sort of divide them into two groups. So some primary functions, which are the things that the kidneys are really responsible for. They're really good at. These are their primary functions. Those include regulating or maintaining or balancing out the pH, the level of ions in the body, the osmolarity. So what is osmolarity? What is osmolarity in your own words?
Water or blood? Water or plasma?
Sort of, yeah. But what is, if you were to describe osmolarity? Basically how salty your blood is, how much sodium is in your blood, what's the concentration of your blood, right? And the kidneys help to balance that. We don't want too much ions, we don't want too little. We don't want too many bicarbonates. That's going to give us an acidic pH. Right? So the kidneys are really good at fine-tuning those things, fine-tuning the volume, blood pressure and blood volume, regulated, as well as removing some of those dangerous, harmful metabolic byproducts like ammonia, right? And nitrogen and urea. Alrighty? And then the secondary functions are going to be things like secreting erythropoietin and renin, which we've talked about, activating vitamin D to its active form, calcitriol, and then gluconeogenesis, which helps the liver do, right? Glycogen. All right, now this slide is to really remind us of what we just talked about. So those two important capillary beds that I asked you to sort of remember, the peritubular capillaries and the vasa recta. The peritubular capillaries coming into close contact or close intimate association with the proximal convoluted tubule, and the vasa recta coming into intimate connection with the loop of Henle. These two interactions or associations are very important with regard to reabsorption and secretion. Right. Now, we're going to talk about the movement of processes across the tubule and the blood vessel. Glomerular filtration, right? That's the first step in this process. We have blood that is coming to the glomerulus via an afferent arteriole. That blood is going to be filtered across the glomerulus into the Bowman's capsule. And then the remainder of blood that has not been filtered out, or substances that are not filtered out, such as proteins, red blood cells, are going to continue on into the efferent arteriole and back into the systemic circulation. Then we have reabsorption, where substances and water is moving from the proximal convoluted tubule back into the blood vessels. All right, so think about you filtering this blood, creating a filtrate here, and then your body saying, hey, wait a minute, I actually want some things back from that fluid. So I'm going to take them back. That's what reabsorption is. I'm going to take those things that I accidentally filtered out that I actually really think I need, like proteins, like glucose, like some sodium, like some chloride, lots of water, right? Things I don't think I want to lose, but they happen to have been filtered out. I'm going to grab those back from the proximal convoluted tubule into the peritubular capillaries. Likewise, secretion takes place as well. You filtered some things out, but there are excess things that are still in the blood that you'd like to get rid of. Drugs, toxins, excess ions, excess calcium, excess chloride. Those things need to be rid, or those things need to be secreted so that they can enter that filtrate and become a part of the urine. Right? So essentially, reabsorption and secretion are the same process, movement across these two membranes, but they're happening in opposite directions. Right? And lastly, excretion happens from the tubules out of the body. So excretion is where we have the final filtrate, right? That final fine-tuned substance which leaves the calyces, enters the ureters. This is called the final filtrate, which we call urine, and that happens, that is removed from the kidneys by excretion. Now, excretion differs from elimination, and we'll talk about elimination with the GI system, but excretion implies that something was taken from this substance. Okay? But it differs from elimination, which happens with the gastrointestinal products, and that is just removing of waste products, right? Excretion versus elimination. We'll talk about that as we move on. Okay, so this image is really helping us solidify those three exchange processes and make sure we understand where they take place across the nephron. So again, filtration happening here. We create a filtrate which now sits in the Bowman's space, in the Bowman's capsule. And as that filtrate moves across different parts of the tubule, we have different things taking place. Right? In the proximal convoluted tubule, we have reabsorption happening into the peritubular capillaries. This is where the body's saying, hey, I want those things, I'm gonna grab them back. We have secretion taking place in the distal convoluted tubule. This is where the body's saying, hey, wait a minute, you forgot these things, let me dump them into the filtrate really quickly. All right, so we have reabsorption and secretion. And then finally, after we've fine-tuned this filtrate to death, we can then get rid of it via excretion. Okay. Let's keep moving here. Any questions on that part so far? So that's in the big picture. What we're going to look at now is filling in the details, exactly what happens on a biochemical level at each point in the tubule. All right, let's talk about the glomerular filtration. Now, the glomerulus moves the blood volume, basically, again, protein-free, right? So we're not moving proteins here, or we shouldn't be, based upon the size of the glomerulus. So we're moving everything else in the blood, with the exception of blood cells and protein, and we're moving them through the glomerulus into the Bowman's capsule. We do this to 125 milliliters of blood every day, or every minute rather. That gives us 180 liters per day. So that's how much of our blood is filtered across the glomerulus. And that is our GFR. GFR stands for glomerular filtration rate. This is a very important number, not only in terms of understanding the physiology of the kidneys, but clinically, in terms of determining the overall output of how well the body's functioning. Mm-hmm. So the GFR looks like 125 milliliters per minute, and that's how much blood is filtered by the kidneys. That's a big number. When you look at dialysis machines, they don't come anywhere close to being this efficient. And that's sort of the magic with the kidneys. We have these two amazing organs which perform some extremely complex physiology. They're very small, like very space efficient. But if you were to look at some of the machinery that does the job of the kidneys, they'll take up this entire room. If you walked into a dialysis ward, you see lots of big machinery, and they're all doing the job of these two small organs. Right? It's pretty amazing. All right, so let's look at exactly what happens as blood moves across the glomerulus, right? So that leads us to understanding, or to talking about the structure of the glomerulus. So there are three membranes that this blood has to pass through. It has to go through the capillaries, right? That's the first membrane, and that makes sense, right? The blood is leaving a vessel. It's leaving a capillary. So the first layer it has to cross is getting out of that capillary. Now, there are different types of capillaries, and the capillaries of the glomerulus are fenestrated capillaries. What do you think fenestrated means? What do you think fenestrated means? I think I'm hearing it somewhere here. Right, it has holes. So there are different types of capillaries, and fenestrated capillaries specifically have large holes in them. And they're designed that way for purposes like this, to allow certain substances through and others not. So they act like a sieve, essentially. The second layer that this blood has to pass through, or this plasma, is the glomerular basement membrane. So this is the basement membrane of the glomerulus, right? And that sits between the Bowman's capsule and the glomerulus itself, the fenestrated capillaries. The third layer that this plasma has to go across is the visceral layer of the Bowman's capsule, or the visceral layer of the glomerular capsule. All right, and so, oops. And so if we were to look at the glomerulus, again, think about this ball of capillaries that's been stuffed up inside this capsule. And the capsule actually has two walls. It has a visceral wall, which is coming in close contact with the capillaries. And then it has a parietal wall, which is sort of outermost. And in between those two walls is a space. That's where the filtrate is going to sit until it moves into the tubular structures. So basically we have blood or plasma moving from the vessel across the Bowman's capsule, across the fenestrations of that capillary, across the slits in the visceral layer of the glomerular capsule. And it's going to move its way into the Bowman's space, right? And that is going to be continuous. If you look at this part, the Bowman's space is continuous with the first part of the tubule, which is the proximal convoluted tubule. So really what we have here is three layers of structures which are setting themselves up to allow certain things to come out of the blood and other things to remain behind. And I keep pointing those out. Proteins and red blood cells do not move into the filtrate. Right? They should not be in the filtrate to begin with. So when we're talking about fine-tuning that filtrate, we should not have to include the movement of protein unless there is some sort of pathology, and we should not have to include the movement of red blood cells. All right, so let's continue looking at the structure here. So what I want you to understand on this slide is how this three-dimensional layer actually looks. So we have the capillary endothelium, right? This little snapshot here sort of shows it. We have the capillary endothelium, and we can see these little holes in this capillary. This is a fenestrated capillary. The second layer here is the basement membrane of the glomerulus, which is the final sort of connective tissue layer on which the glomerular capsule rests. The third layer here is the glomerular capsule, specifically the visceral layer. So let me jump back here. There are two layers. There's a parietal outermost layer, and then there's a visceral layer that comes very close contact with the actual glomerulus. So you can see them here. Blood is going to go out of this vessel, across the capillary, across the Bowman's capsule, and it's going to squeeze in between. Can you see these little slits? These are called podocytes. So these have little filtration slits that are running in between them. Think about your fingers, right? If you're holding up your fingers, the actual finger will be the podocyte, and the spaces in between will be your filtration slits. So this is exactly where molecules are passing. This is why proteins don't pass. One, they cannot get to the fenestrations in the capillary. Two, they would not get through the podocytes, or the filtration slits. So basically, this whole apparatus is a big sieve. It's letting some molecules through along with the plasma, and proteins and red blood cells do not go through. All right, so now that we're talking about the movement of fluid or the movement of blood, this brings us to talking about Starling forces. So this is what you would have looked at with Dr. Schrader, right? You would have talked about the hydrostatic pressures versus the oncotic pressures, right? Interesting stuff. And so here we have to understand that there are two opposing forces that are either pushing or pulling blood, plasma in this case, right? Plasma or blood. And let's look at those forces. Well, actually, let's talk about them first and then let's draw them out. And let's try to do some calculation as well. So the first force we have is the glomerular capillary hydrostatic pressure. The glomerular capillary hydrostatic pressure. Now, what does hydrostatic pressure mean? What is hydrostatic pressure? All right, it's a pushing force based upon the fluid that's in this vessel. Okay, so that fluid being in this vessel exerts a certain push when it wants to go across the vessel membrane, all right? What about the Bowman's capsule oncotic pressure? That's going to be a pull, right? When we hear oncotic, we think about a pull. Oncotic pressure is caused by the proteins that are present on either side of the membrane, and they're doing pulling. They want to sort of dilute themselves. So they're going to pull water or fluid towards themselves. So hydrostatic is the push, and oncotic is the pull. Now the trouble comes here because we have those forces existing on either side of this membrane. So we have those forces existing in the Bowman's capsule, and we have those forces existing in the capillaries, in the blood vessels of the glomerulus. Alrighty? And so those two forces are acting against each other in certain instances, and we have to try to figure out what is the overall glomerular filtration rate, or filtration pressure, excuse me, depending on those different forces, those different volumes. So let's just draw this out a little bit and talk about how we can calculate these pressures. Right. Right, so glomerular filtration pressures. Let's just draw our glomerulus here. We got our vessels, we have our afferent arteriole. Then we have our capillaries. And then we have our efferent arteriole. All right, and so the direction of blood flow is going to be from afferent into the glomerulus, again, which is our tuft or our ball of capillaries, and then out into the efferent arterioles. Okay. Now, closely adhered to this structure, we have, what's the name of this structure? The Bowman's capsule. Yeah, the Bowman's capsule. Okay. And so just to remind ourselves, the three layers that this, so draw this here. The three layers that this blood or plasma has to move through in order to get into the Bowman space. The fenestrations of the capillaries, the basement membrane of the glomerulus, and then the visceral layer, right? There's two layers, the parietal and the visceral layer of the Bowman's capsule, right? And then we're gonna have this filtrate sitting in the Bowman space. Now let's talk about the pressures here. Right, this continues on to become the proximal convoluted tubule, et cetera, et cetera. Let's look at our pressures. So the hydrostatic pressure in the capillaries is going to be represented by this, right? So let's write it out. Right, so remember, so the hydrostatic pressure is a push, and the oncotic pressure is a pull, right? Which is caused by proteins. This push is caused by the fluid. And so when you actually look at the pressures here, we have the pressure, the hydrostatic pressure of the glomerular capsule. This is the push that's exerted from the vessel where this blood or this plasma wants to go across into the glomerular, into the Bowman space. So this is going that way. the hydrostatic, can you guys see that? I'll make it a little bigger, PGC. And that is going across this way. Then we have the oncotic pressure of the glomerular capsule, just sort of represented like this. And what direction is that having a force in? The oncotic is going to be pulling, right? So we want to pull fluid from the Bowman space into the glomerulus. Okay. Very similarly, in the Bowman space, we have the oncotic pressure of the Bowman space, or the Bowman's capsule. I'll say the oncotic pressure of the Bowman's capsule. And then we have the hydrostatic pressure in the Bowman's capsule. Now, what direction do you think the force of the hydrostatic pressure in the Bowman's capsule would be? It's going to be pushing right back into the glomerulus, right? What about the oncotic pressure of the Bowman's capsule? We said proteins that want to do what? Pull, right? So it's going to be pulling fluid this way. I'm sorry, this is getting a little messy, but I hope you can see that. So we have the hydrostatic pressure of the glomerular capsule exerting a push across this membrane. We have the hydrostatic pressure of the Bowman's capsule exerting a push in the opposite direction, back into the glomerulus. We have the oncotic pressure of the glomerular capillaries going from, again, pulling from the capillaries, from the Bowman space to the capillaries. And then we have the oncotic pressure in the Bowman's capsule, which is, again, pulling fluid from the glomerulus over into the Bowman's capsule, or the Bowman space. Okay? And so when we look at these pressures, we can determine the overall glomerular filtration pressure by sort of calculating all of these pressures. So let's do a little bit of an equation here. So we have the hydrostatic pressure of the capillary, let's say that's 60 milliliters of mercury. Let's say the hydrostatic pressure of the Bowman's capsule is 15 millimeters of mercury. All right. Let's say the Bowman's oncotic pressure, let's see, the glomerular capillary pressure here is 29. What would the oncotic pressure in the Bowman space be, in the Bowman's capsule? 0. Why is it 0? Why is it 0? It's sort of a trick question. This has to do with something I've been saying all along. Why is the oncotic pressure in the Bowman's capsule 0? We're not, it has to be protein, yeah. So we're not pushing because it's oncotic pressure. Good, there's no proteins in the Bowman's capsule, or there shouldn't be any. And so because we have an absence of proteins in the Bowman's capsule, the oncotic pressure, or the pull in the Bowman's capsule, is always going to be 0. There should be no protein in the space. Alrighty? And so the push, or the pull rather, the pull from the Bowman's capsule should always be 0. There should be no protein in this space, or in this filtrate. And so I want you to sort of work on this, try to calculate this and see what you get for the GFP, the overall glomerular filtration pressure. Right, so you're basically minusing the hydrostatic glomerular pressure, you subtract the hydrostatic Bowman's capsule pressure, and then you subtract all of that. You take all of that and subtract the oncotic pressures. Does anyone get a figure? 16, yeah, that's correct. So 16, if you take 16, we minus 45, and then we minus 29 from that 45, we get 16. So that's our overall glomerular filtration pressure, 16 millimeters of mercury. Does everyone understand how we got